If you're tuning into this video, that should mean that you've gone through the derivatives of all types of parent functions along with having a basic understanding of the chain rule. My aim in this video is to solidify your understanding of the chain rule because it's the single most important concept in differential calculus, and it'll make or break your success when you try to tackle implicit differentiation, which is the foundation of related rates, which comes a few sections down the road for you. As we know, the chain rule helps us quickly take derivatives of compositions of functions without the use of the limit definition for the derivative. So let's go ahead and take a look at the yellow here, where we have the derivative with respect to x of f of g of x. As I've stated before, and I'll state again, the derivative of f of g of x with respect to x would be the derivative of f while leaving the input the same, so f prime of g of x, multiplied by g prime of x. But in this video, I need to show you how the chain rule always applies. It always does, and you need to keep that in mind because, like I said, this will give you a lot of trouble later on if you don't solidify this now. So if we're taking the derivative of a composition, yes, you know that as f prime of g of x times g prime of x, but we need to take it a step further. Here's what I mean. We are going to take the derivative of the inside, because you see how there's a parentheses around g of x, there's a parentheses around x. And so we can multiply by the derivative of x with respect to x. Yes, obviously, that will reduce to 1. But it's important to note because later on, you won't always be taking the derivative of x with respect to x. This might be y. And so it'll be important to note that. It won't be redundant in that case. But for now, this is redundant, stating dx over dx. But it needs to be shown. So similarly, up here, let's take a look at the derivative with respect to x of f of x. This would be f prime of x. And then we would multiply by the derivative of x with respect to x, or the derivative of the input with respect to x. Yes, again, this will reduce to 1. But it's important to note. It's very important to note. Another thing here. So the derivative of x, or the derivative of f of g of h of x with respect to x. If we understand that power rule, or the chain rule, remember, we take the derivative of the outside while leaving the inside the same. All right, so now I'm going to dive into this and really solidify your understanding. So take the derivative of the outside and leave the inside the same. Then you will take the derivative of the inside. So in taking the derivative of the inside, notice that we'll have the derivative of g of h of x, which is another composition. Again, if we're taking the derivative of a composition, do not be afraid. Just go ahead and trust the process. Just take the derivative of the outside and leave the inside the same. Again, now, okay, cool. And then afterwards, multiply by the derivative of the inside. Multiply by the derivative of the inside right here. And so, then the derivative of that would be h prime of x. And then we need to go ahead and multiply by the derivative of the inner, the last part there, that input, or x, which would be the derivative of x with respect to x. Again, this will reduce to 1. But I want to take a moment here and just show you here that when we have, it doesn't matter how many chains or how many levels we have, as long as we trust the process and take it one at a time, you can solve really any derivative involving chains or levels in one line. Anything after that will be algebra in terms of simplifying, but you really only need one line to actually compute the derivative. Because here we have 3 levels. All I did was start off by taking the derivative of the first level, leaving the rest the same. Then you go inside, so now we have g of something, or g prime of that something, leaving the inside the same. Then we take the derivative of the inside, which is h of something, so that would be h prime of that something. And then we multiply by the derivative of the inside again, which would be the derivative of x with respect to x. So one more time. We have f of g of h of x, or what I saw was I have f of something. If I'm taking the derivative of f of something with respect to x, that'll just be f prime of that something. Then you multiply by the derivative of that something, which is g of something. So then the derivative of g of something is g prime of that something, and then you multiply by the derivative of the something. And then, okay, cool. Now this is h of something. So the derivative of h of something is h prime of that something. Then we take the derivative of that something with respect to x. And because it happens to end at dx over dx, that is where we stop. That is where we stop. So hopefully this makes some sense here. This is only a portion of this video. This is just the introduction. Now what I'm going to do next is I'm going to go ahead and show you how to identify levels in every single type of parent function that you'll see. So to start off, let's go ahead and start off by re-solidifying that power rule. So for example, let's say we're taking the derivative with respect to x of x to the n. We found earlier that yes, this will be n times x to the n minus 1 because we utilize that power rule. We will drop the power and then we will subtract 1 from that power. Just like that. But remember, it's important to be redundant here. It's very important to be redundant and just include that we need to multiply by dx over dx, or the derivative of the input with respect to x. Because it happens to be x here, this happens to reduce to 1. But let's go ahead and look at another example. And let's say we're taking the derivative with respect to x of, let's go ahead and say something raised to the n power. This is how we can identify our level here with the power rule. If it's a parentheses and then outside of the parentheses there's that power, well, here's what that looks like. If we were looking at a composition, f of something, well, look at that. The function is on the outside. So we are performing a power on something. And this something could be anything. This could be a smiley face for all we care. And I'm going to go ahead and use that smiley face because it's important. So the derivative with respect to x of something to the n power would be equal to n times that something now raised to the n minus 1 power multiplied by the derivative of that smiley face or that something with respect to x. And this could be anything in there. It could be 5x, sine of x, doesn't matter. We're just stating that we are taking the derivative of whatever the inside is with respect to x because that's how the chain rule works. That's how it works. So up next, let's go ahead and take a look at our trig functions. So for example, what if we were trying to take the derivative with respect to x of sine of something? And again, I'm going to go ahead and put a smiley face in there just to represent anything. I'm just using this to overemphasize it. Again, remember, functions are f of something. You're performing a function on the input. You're performing the sign on this input. So sine would be on the outside no matter what. No matter what. And so the derivative with respect to x of sine of something would be cosine of that something, because that's how the chain rule works. You're taking the derivative of the outside while leaving the inside the same, and then you multiply by that something, the derivative of that something. It's all about parentheses, about what you're performing a function on. And so let me go over another example that confuses a lot of my students personally. So let's go ahead and say we're taking the derivative with respect to x. Let's say we're doing sine cubed of, let's say, something. So sine cubed of something. Now here, let me go ahead and just stay coordinated. So here, this is where a lot of my students get confused. A lot of my students would go ahead, or some of my students would go ahead and say that this is equal to, well, that's going to be, okay, that's going to be cosine cubed of something times the derivative of something with respect to x. Nope, not at all. So when we have this cubed here, what we need to do is, look, we have a trig function that's cubed, and then that. We need to rewrite this so that we can properly see the levels. Because we can rewrite this as the following. As the derivative with respect to x, parentheses, sine of that smiley face or that something, all raised to the third power. And I'll go ahead and use purple to identify that. And so there we go. This is my outermost level because it lies on the outside of the parentheses. We are performing the cube of whatever this is. And so this is our outer level. So to take the derivative of something cubed would be 3 times that something now raised to the second power. And what we can do now is we can go ahead and replace everything that we got again. And again, let me stay consistent. Let me just go ahead and use blue for that. So the sign of that something. And you just replace the inside. Then you multiply by the derivative of the inside. So then you would multiply by the derivative of sine of something. So notice here, sine of something. Look at this parentheses. Let me overemphasize that. This separates the levels because we're performing the sine of something. So the derivative of sine of something is cosine of something. And we can go ahead and place that something back in there. Then lastly, we would multiply, and I'm sorry I don't have enough room, but we would multiply, and actually I do have enough room. Let me just scroll to the right. And so then we would multiply by the derivative of that something. We would multiply by derivative of the happy face with respect to x. And the reason that this doesn't reduce to 1 is because we don't know what the rate of change of the smiley face is with respect to x. But if we were taking the derivative of x with respect to x, well, that's basically saying how fast is x growing compared to how fast x is growing? Well, it grows at the same rate as the rate it's growing. I hope that sentence, that phrase just made sense. That's like saying, I am the person that I am. Yeah, that's true. Dx over dx, it's like 5 over 5 or 10 over 10. Yeah, that's just 1. You're comparing the growth of x compared to x. Well, it's the same thing, so it's 1. And I know I sound like a broken record, but I am going to overemphasize this till I die. All right. So now that we're back here, but this is it. We can complete any derivative involving the chain rule in one step, in one line. We don't have to waste paper as long as you understand how to properly identify your levels. And the common misconception here is when we have a trig function raised to some power. You're going to have to be able to, for now, rewrite it in terms of parentheses, then sine of something all cubed or whatever power. And then eventually, you'll get used to it and you'll know that, okay, cool. I got the derivative with respect to x of sine cubed of this. All right, cool. We're taking something cubed. So that's going to be, all right, let's go. 3 sine, smiley face, squared, multiplied by cosine of that smiley face, and then the derivative of that smiley face with respect to x. I promise you, you will get this good, this quick at it. I promise you, but you have to be able to trust the process and continue practicing it, because if not, then this is all a waste. So let me go ahead and run through another example now. This one's, again, it's trig. So let's say we're taking the derivative with respect to, let's say, t. So the derivative with respect to t of, let's say, secant of x. So notice, okay, identifying levels. There is no parentheses that is clearly shown, but we can go ahead and just put a parenthesis right here because we're performing the secant of x. Secant of x. So the derivative with respect to t of secant of x, well, we're taking the derivative with respect to t of secant of something. So the derivative with respect to t of secant of something would be secant of something times tangent of that something. And then afterwards, we will multiply by the derivative of that something with respect to t. And so now we're just going to go ahead and fill everything back in that we had. We're going to fill in our input everywhere. So that'll just be secant of x, tangent of x, and then x. So we have the derivative of x with respect to t. This will not reduce to 0. This is dx over dt, or the change in x with respect to t. Do not get your units confused. Identifying your units is the most important thing in the chain rule because, again, it's going to help you with implicit differentiation. I don't think it's that hard to grasp, but it should be noted that we need to make sure we know how to do this. All right, now it's even more important to note, let's go ahead and dive into logarithms and exponential functions. So let's say we're taking the derivative with respect to, let's say, r of, let's say, some logarithmic function. So log, the base is some constant. I'm going to name that a. It's just a constant. It's not a variable, so don't be afraid there. And the argument is, we can go ahead and say it's t. So let me go ahead and use t for that. All right, so let's go ahead and get to business. So if we're taking a derivative of a logarithm with a base of a of something, this will be, so remember that those rules for the derivatives of logarithms, we will have 1 over the input, so that t, we'll have that input there, multiplied by the natural log of the base, which is a. And if it was e, that would just reduce to 1, as a reminder. I'm using a as just a general guideline for everything. And then afterwards, we apply that chain rule. We apply that chain rule and multiply by the derivative of the argument with respect to whatever it is we're taking the derivative with respect to. So that would be dr. So the derivative of t with respect to r. And just like that, this shouldn't be too difficult to wrap our heads around, but it just takes consistency to master this. And next up, if we're tackling logarithms, let's go ahead and tackle exponential functions. So let's say we have the derivative with respect to, I don't know, let's go ahead and say m, the derivative of something with respect to m, and that something just so happens to be a raised to the, let's say, y power. So we have the derivative of a to the y with respect to m. So here, a is a constant. We need to go ahead and note that, what our constants are and what's changing. So on the side here, I'm going to go ahead and note that a is a constant. Also going to note that we're taking the derivative with respect to m. So that's obviously a variable, but we need to note that y is a variable, or it's changing. It's important to note that it's changing. So for it to be a variable, that means that it's changing. It's not constant. Hopefully that makes sense. So then if we're taking this derivative, well, we're going to trust that process. The derivative of a to some power, because we can go ahead and wrap this in a parentheses. So we're performing an exponential function. So that means that we have a to some power. So the derivative of a to some power is equal to the, okay, boom, we repeat the function. So a to some power again. Up next, we multiply by the natural log of the base, or a in this case. And then afterwards, again, we apply that chain rule and we multiply by the derivative of that something with respect, here it's m, so this would be with respect to m. And again, this will not reduce to 1. It will not, because we're taking the derivative of y with respect to another variable. So we don't know what that is, and so we can't reduce it to anything yet. If we were told that y equals, let's say, 2m, well, yeah, then that would be the derivative of 2m with respect to m, which the derivative of 2m with respect to m would be 2 in this case. And so to finalize this video, let me go ahead and just give you some ridiculous example. This probably isn't really a function, but let's say we're taking the derivative with respect to x of, let's say we're doing the natural log of, let's say we're doing sine cubed of 4x squared plus 3. Something ridiculous like this. I doubt this is a function, but let's just go ahead and say we're taking the derivative of this with respect to x. So again, we want to go ahead and just start off by identifying our levels. All we need to do is concern ourselves with the first level and then the rest. So this would be our first level. We're taking the natural log of something. We're taking the natural log of something. So what this means is that the derivative with respect to x of the natural log of something, well, that would be 1 over that something. So we repeat the argument. So whatever that something is, and I'll go ahead and write it in yellow. So that'll be sine cubed of 4x squared plus 3. And then we multiply by the natural log of the base. In this case, since it's a natural logarithm, we'll be multiplying by the natural log of e. And we all should know by now that the natural log of e is 1. But we're going to go ahead and leave it just to overemphasize our point. Next, we're going to multiply by the derivative of the inside, or the derivative of the argument. So what's the argument? Well, let's identify it. It is sine cubed of 4x squared plus 3. Okay, how do we identify the level here? Remember, we're taking the sine of this, and then we're taking the cube of it. So the way we can rewrite this would be the sine. So let's go ahead and use red. So this would be the sine of 4x squared plus 3, then cubed. So let me go ahead and just erase this over here. That way I can overemphasize that point. Then it's cubed. Then it's cubed. All right. And let me just go ahead and put that back there along with the yellow. And there we go. So this is our next level. We have something cubed. Something cubed. So we already took care of that, the natural log part. We're good. Now we worry with the derivative of something cubed. Well, the derivative of something cubed that's going to be 3 times that something squared. And then we multiply by the derivative of that something. We multiply by the derivative of that something. And what's left on the inside? Well, the inside was sine of all this good stuff. Was sine of this. So let's go ahead and just replace everything back in. So in red, let's just go ahead. We had something cubed, or sine of all this. Sine of 4x squared plus 3. Boom, just like that. Just like that. And now next, we need to identify the next level, which I said was sine of something. Sine of something. So we're going to multiply by the derivative of sine of something. That's going to be cosine of something. Cosine of something. And then we multiply by the derivative of what that inside was, or what that something was. In this case, that something so happened to be 4x squared plus 3. And so let's go ahead and fill that all back in. 4x squared plus 3. And then if we multiply by the derivative of 4x squared plus 3, well, this looks like the end of the road, because the derivative with respect to x of 4x squared plus 3, the 3 is a constant, that would cancel. 4x squared, that would be 8x. 8x. And if we really wanted to be redundant, well, that's actually 4 times something squared plus 3. And so afterwards, we will need to multiply by the derivative of that next something. So that would be the derivative of x with respect to x. And this, again, guys, that would be redundant to state in this case, solely because it's the derivative of x with respect to x. But had that been a y or an m or a p or some other name for a variable, we need to go ahead and always emphasize that. And so this is the end of the video. I hope that after this quite long video on this topic really helped you out a little bit, because at the end of the day, if you don't understand chain rule, you're not going to be in a good place when you move into the next series on related rates and analyzing and applying that derivative. So please, please, please continue to practice the chain rule. This is the most important rule that will continue your knowledge into calculus. So watch the next videos in terms of the examples that I'm going to show you, how to work them out. But again, the process is the same for all of them. So until next time, I'll see you. Keep practicing.